Let's look at another problem where we try to simplify R, that is, come up with a region S that's easier to work with. In this particular case, we have this rectangle that's rotated. And what we're going to try to do is analyze this so we can actually determine a transformation that will give us an S that's very simple. So how do we do that? Well, segments are usually much more simple to work with as opposed to more elaborate curves. So, for instance, when we look at this segment and its opposing segment, I'm going to, as you see here, I'm going to use the red color. And we look at this segment and this segment, I'm using the blue color to keep them separate. So we're just going to do some Algebra 1 here, or basically general math. When you see these 2 points here and you compute rise over run, you get a -1. And of course, we've got a very simple point right here, 0, 1. So let's just compute the line that contains these 2 points. We'll use point slope. So we'll have y minus 1 equals what? -1 times x minus 0, which is that equation there. And then just to simplify it, I'm going to put all the variables on one side of the equation. So transpose and then move the constants to the other side. We get x plus y equal 1. So very simple. This equation satisfies these 2 points. We have what we need. Now, we don't have to do that again because as we move from this point to this point, we see that the x value is increased by 1 and the y value is increased by 1. So we have translation in both variables, x and y. So using the translation theorem, we simply replace x with x minus 1 and y with y minus 1. And so we have this equation becomes this equation. And then, of course, we have a -1 and a -1, which gives us a -2 transpose, and we get x plus y equal 3. So we have 2 very simple equations, and now you can see that we have a definition for our u, but let's hold off on that. Now for the other segments. Notice here, 1/2, 1/2, 3/2, 3/2. You do the rise over run, you get 1. So we have a slope of 1, and to make it really simple, or to think of this in a way that's easy, notice the x's and the y's are the same. So that's just the line y equal x. So even though we have the slope m equal 1, we just have y equal x. And so in this case, just to parallel this, I'm going to subtract x from both sides. I have y minus x equals 0. Okay? So again, a very simple illustration of how you can compute the line just using basic algebraic methods. Now, what we want to do here is compare this point and this point. Notice, in this case, that the x value is decreasing by 1/2 and the y value is increasing by 1/2. So we'll do translation in x and y. So for the x, we replace x with x plus 1/2, and for the y, we replace y with y minus 1/2. So this equation becomes this equation. Now when you look at this, we have a minus 1/2 and we have another minus 1/2, which is -1. When we transpose, we get y minus x equal 1. So now again, we have 2 simple equations. So this is a very, very straightforward way to produce a transformation. Now, of course, how I've decided to rearrange these equations does not matter. You can do a different rearrangement, but still have a worthy transformation. So the transformations are in no way unique, but it doesn't matter. So now what we're going to do is we're going to define u to be x plus y, and we're going to define v to be y minus x. So we'll have a transformation from the xy plane to the uv plane defined this way. Now, the beauty of all of these boxes here is that we see that the u runs from 1 to 3, giving this compound inequality, and the v runs from 0 to 1, giving us this inequality. So this automatically gives us our explanation of S, or representation that is, in the UV plane. So again, U runs from 1 to 3, V runs from 0 to 1, and we get this nice rectangle here. Now I don't have to go through the fact that these segments are converted into segments. I did that on the last problem. I'm not going to do that again. So we're going to understand that segments are mapped into segments under linear transformations. Now I said compute, so we've got our S. Now I said compute the Jacobians. So now what we can do is do the Jacobian here. That is where we're looking at u and v as functions of x and y. So this is the definition for the Jacobian. So basically we're doing u, partial of u with respect to x, partial of v with respect to x. So that's going to give us a 1 and a -1, which you see in this column. And then we have the partial of u with respect to y and the partial of v with respect to y. So we get the 1 and the 1, this column. When you do the determinant crisscross, you get 2. And the remaining determinant for the other transformation, which in this case is the inverse transformation, we didn't compute, but we don't need to. We know that these two Jacobians are just multiplicative inverses. So this Jacobian for the inverse transformation will just be the reciprocal of 2, which is 1/2. And we are done.